All right, and welcome back, everybody. We are down to our final two videos, I believe. So, we are going to try to end on a strong note here by showing a little bit more of what we know about chaos and chaotic dynamics in particular. So, we need to finish our discussion of what we saw in the previous video, talking about how we are trying to transform a problem about the logistic map from the strange attractor in that setting to a completely different phase space, which we did in the last video, right? We showed that these two sets, lambda and sigma, when we think about them as metric spaces, are actually equivalent. They define the same objects from a metric standpoint. They do the same things topologically. So, what we would like to do now is show that not only do we get that these two phase spaces are the same, but that these two maps, right, whatever these maps are exactly, like this F map, right, the logistic map for R values greater than 4, is what we call conjugate, right? You'll remember this. We're going to say that this logistic map is conjugate to to this map sigma that we're going to create, little sigma, on the sequence space sigma of binary sequences. So we are going to find this sigma. We're going to define sigma so as to be equivalent to F. So F is going to have its own dynamics. The logistic map is going to have its own dynamics on the strange attractor lambda. Right? We didn't show it's a strange attractor yet, but it is. It will. We will show it. So on this set F, or on this set lambda, F has a certain set of dynamics, and those dynamics are actually going to be equivalent to the dynamics that little sigma is imposing on our binary sequence space. And that one should be a little strange. Like, how can we do that? How do we know that these two maps have the same dynamics? And we're actually going to go through the entire argument here. So we first need to define that sigma, and if you've been looking at the bottom of the page, you already know what the map is going to be. We are going to create something called the shift map, and this is going to be a left shift. Left shift or right shift? I can never remember. The point is, we are going to shift our indices to the right by 1 in each of our binary sequences. So we are effectively going to take this sequence, and remember S0, S1, S2, S3. These are either zeros or ones because we're working with binary sequences, right? The symbols in symbolic dynamics are the 1 and the 0. So we are just taking two sequences of two objects. But what we're going to do here is we're going to take that sequence and chop off the first term. We're going to just completely omit the S0 term in the sequence. So what winds up happening here is we create the shift map. And what the claim is that sigma and F, the shift map, is conjugate to the logistic map, and we will show it in detail. So just as an example to show how that shift map works, we can go ahead and take this alternating sequence of 1s and 0s and just say, okay, forget about it, start at the 0, and that's how we wind up with this shorter sequence. Technically it's shorter, but they have the same cardinality. But there are, let's say, we can note that there are 2 fixed points to this shift map, and that's reminiscent of the fact that the logistic map has 2 fixed points for this regime when R is not equal to 0. So these 2 points, 0, 0, the sequence of zeros and the sequence of 1s, correspond to the itineraries of the 2 fixed points, either the origin or wherever the non-trivial fixed point is on the logistic map, right? We only get 2 of those, right? We should only expect 2 of those. We can also note that this shift map is not invertible, right? In fact, it's not 1-to-1, it is a 2-to-1 map. There are 2 sequences that map to the same shift, right? And it just means that you either chopped off a 0 or you chopped off a 1, but once you map it through the shift map, you don't know which one produced it. So either you started with this guy or you started with this guy, but they still produce the same sequence. So we just need to make sure that we don't, when we're talking about using sigma as a function, we acknowledge that sigma doesn't have an inverse. So we do need to be very careful. And this is, once again, reminiscent of the fact that F, the logistic map, doesn't have an inverse. Right? This guy is, once again, 2 to 1 almost everywhere. All right, so we can also note here that it's actually really easy to show that this sigma map, the shift map, is continuous on the sequence, on the space of binary sequences. Right, so we can show that it's continuous at any sequence S of sigma. So we're going to choose an arbitrary S, and well, for continuities, for a proof of continuity, you need to have an arbitrary epsilon, and you need to find a delta that will get you within within that epsilon tolerance in the image. So we're going to choose our sequence, our index, so large that 1 over 2 of the n is less than whatever that epsilon was. We can do that, right? Remember, this is going to be Archimedes' principle working for us again, that we can do this. And we're going to take delta to be 1 over 2 to the n plus 1. Right, so this will be how far apart sequences are allowed to be in order to map forward and be less than epsilon away from one another after the shift. So for any sequence, any other sequence here that is within delta of S, that would have to mean, like by definition here, remember, these this delta is equal to 1 over 2 to the n plus 1. We had a lemma in the previous video or two talking about, oh, come on, oh shoot, I'm almost there, I almost had it. We had a theorem in the previous video telling us that if we made that observation that the distance between a pair of sequences was actually less than 1 over 2 to some power, then we know that these two sequences have to share the first k or first n plus 1 entries here. They have to share the same initial itinerary, so to speak, when we relate this back to the lambda set for the logistic map. So we would then observe that if we map t through the shift map, that we actually get what t. Oh, there's a missing index in there. For shame. There's a t1 and then a t2. Okay, there we go. So if I were to shift t forward by 1, then t1 is equal to s1, t2 is equal to s2, and so on until I get to tn plus 1, which would be equal to s sub n plus 1. So if I take the difference then between sigma of t and sigma of s, right, those two sequences agree in the first n components, which would mean, by our previous lemma, that they can be no more than 1 over 2 to the n apart in sigma. Therefore, by our choice of n, right, the choice of how far out in our indices we have to go, being less 1 over 2 to the n being less than epsilon, that means that we have mapped within the correct distance. So this map is continuous. And that's actually simpler than the proof that we had in the previous section. So we're already seeing, we're already receiving dividends on our choice to switch into a different phase space, a different metric space. And now for the real payoff, it's the periodic orbits and the ability for us to write out specific elements of this phase space in the sequence space that makes this switch into sigma much more beneficial to us than working with the lambda phase space. We can represent all of the periodic orbits by just creating sequences. Right? We can say, okay, I can actually explicitly tell you how many period 1 or fixed point solutions I have. I can tell you how many period 2 solutions I have, period 3. Right, I can show you all of these. I can explicitly write them down, and that is the power of this method, of this of switching into this space. These guys are much, much easier to work with than the elements of lambda, because frankly, we really we're going to have a really hard time expressing what those elements look like on the interval from 0 to 1. So much easier. This is a lot easier to work with sequences than it is to work with lambda. So our goal, remember, is to show that we can complete this commutative diagram. Right? We want to show that no matter where I start on this diagram, so let's say I started here, if I go down and over, that has to be the same thing as me going over and then down. Or if I started at a different location, if I started down here, well, I can go backwards through the homeomorphism S and then forward through lambda, or I can go across sigma and then back up through S. Right? There are a lot of ways to express this, but we just need to make sure that function compositions agree with one another. It doesn't matter which order we take them, just so long as if you start and end in the same spot, then it doesn't matter how you got to those locations, you will get the same composition function. And this is exactly what we're seeing here in these three statements. So I can either show that, so F here, I can either say that I'm going to start and stop here, or I go down, over, and up. So that would be, reading this backwards, that would be S inverse after sigma after S would be equal to F. And that's exactly what this statement is up here. Sigma inverse after S inverse after sigma after S. Or I could go across that bottom row, and that would be another way that I could try to complete this diagram. So I can go straight across here, or I can go up, over, and back down. So that would be S after F after S inverse. Should be the same thing as going straight across with sigma. Or I could play this game with just completing the, instead of just working with one side, I can go straight across and do, oh shoot, yep, I can go down and over, or over and down. That would be the same thing as me saying sigma after S is the same thing as S after F. And those three definitions, or those three possible avenues, are listed here, right? This is exactly what we're showing. These all would complete the commutative diagram above. And we need to remind ourselves that it's a bit difficult to work with points in lambda. The whole point of this exercise is to move everything into sigma. So we really don't want to be working with any S inverses, because if I'm going against the grain here, I'm going against these S maps, that means that I would be, like the image of S inverse lives somewhere in lambda, and I want to avoid the lambda. So I should only ever be going with S here. So out of the list that I've chosen here, both 1 and 2 use S inverse, but 3, yeah, this one only uses S's. Okay, so we would like to go ahead and demonstrate then that we satisfy this conjugacy relation, that sigma and F are conjugate through S, or via S. Okay, and that's all we're going to show here. This actually is pretty straightforward. This proof is very, very quick. The shift map, again, is conjugate to the logistic map via the itinerary function that we created in the previous video. So let's show this. So we need to show that two functions are the same, right? These two guys are the same if and only if they do the same thing on the same set, right? They do the same thing to each element of the set. So if I am starting with, let's see, which guy do I want to start with? I want to start with the left-hand side. So that means that S needs to take some element of lambda and map it through into sigma. So I'm going to start with some arbitrary x0 that lives in lambda, right? And that guy is going to have an itinerary associated with him. So that's all I'm constructing here. I'm starting with something, that should live in lambda. There we go, much better. So x0 has an itinerary of this sequence, and this sequence lives in sigma. There we go, that's better. So if I were to if I were to explicitly map out what that means that x0 lives in s sub 0, and it maps forward into I sub s1, so one of the two sides of the a0 set from the previous video. f2 would map into the I sub s2 interval, and then so on. So what I can then say here is that I know exactly what sigma does to that itinerary. It shifts it and says, forget about the S0 location, just go immediately to what f does to x0 and start there. On the other hand, if I were to take x0 and map it forward with f, then f of x0 is going to map straight into I sub s1, f2 is going to map straight into I sub s2, and so on. So my sequence, the itinerary of mapping this guy forward, is just offset by 1, which is exactly what the shift map did to the original itinerary. And therefore, I have shown that these two functions map to the same itinerary. They do the same thing to the same elements. So these two functions have to be the same. We've already shown that S is a homeomorphism, so that means that we do have an honest-to-goodness conjugacy. So, from a dynamics standpoint, that means that the orbits of the logistic map on this set lambda are mapped directly onto the orbits that the shift map imposes on sigma. So that means that they employ the same dynamics. They exhibit the same dynamics. So the dynamics of the logistic map are identical to the dynamics of the shift map on these particular sets. And I did say it at the top of the video here, I want to show that this shift map, or not the shift map, I want to show that f is chaotic on this non-escaping set lambda. I knew I remember the term for lambda eventually. So I want to make sure that whatever I do, whatever properties I want to show about f, I can actually show the same property about sigma, and then use the conjugacy to show that these two things do the same. These two dynamical systems behave the same. So we need to show that sigma is chaotic, right? So we're going, instead of going through f, we're going to go through sigma. All right, so remember, if we're going to show that sigma is chaotic, we have to show that periodic orbits are dense in the sequence space, that sigma is topologically transitive, and that it exhibits sensitive dependence on initial conditions. And the first two of these we can actually take care of in one proof, so one fell swoop. So let's show that periodic orbits are dense. Okay, great. Choose an arbitrary itinerary or an arbitrary sequence in sigma, and make sure that it begins with digits S0 through Sn. And these guys are going to be, these guys are going to be within distance 1/2 to the n of this repeating itinerary, this periodic orbit. Okay, so these guys necessarily start within some, this sequence S starts out within a distance of 1/2 to the n of whatever periodic orbit shares those first few digits. Therefore, to whatever degree of accuracy I want, my sequence S here is going to be within that degree of accuracy to some periodic orbit. Therefore, I can approximate S via a sequence of periodic orbits to any degree of accuracy I'd like. Therefore, sigma here, the orbits of sigma are dense, little sigma are dense in big sigma. Excuse me. Right, so periodic orbits are dense in sigma. So now consider the following itinerary. We are going to show that, we're going to show transitivity now. So we're going to show that there is an orbit, or there is a sequence that maps arbitrarily close to any sequence in sigma, right? And this is going to be equivalent to transitivity. as far as maps are concerned. There is an element whose orbit travels within whatever degree of accuracy we want to each element of this set, to each element of this space, sigma. So we're going to create the following guy here. So S star here is going to be a very specific combination or very specific ordering of all the different ways that I could create binary sequences of a given length. So a binary sequence of one element is either the 0 or the 1. Binary sequence of two elements is either 0, 0, 0, 1, 1, 0, or 1, 1. And I keep going through this list systematically, and I'll wind up with 8 different binary sequences of length 3, 16 binary sequences of length 4, 32 of length 5, 64 of length 6, and so on. So this S star is going to grow exponentially here, right? We're going to be creating a lot of different blocks here. But the point is that eventually I will hit each block in that sequence. So that means that any given sequence T belonging to sigma will have to agree with S star to any degree of accuracy after some maybe really large number of iterations of the shift map. And to illustrate this, let me give you an idea of what that means. Let's say that we were trying to, let's see, what are we trying to do? We're trying to get close to the period 4 orbit. This period 4 orbit agrees with S star in its first 4 digits, and we can actually see this after the way that I've ordered these guys up here. We are effectively just counting in binary. Is that right? Close. Close. We are almost. Did I miss one? No. Yeah, we are just straight up counting in binary. Yeah. So that's let's see. Let me recenter here. Okay. So the period 4 orbit down here is going to agree with S star in the first 4 digits after 24 iterations of the shift map. So I will take this S star and apply sigma to it 24 times, and I will wind up starting with, so sigma to the 24 of this guy, not of that guy, no, of S star. This guy is going to begin 1, 0, 0, 1, and then other stuff is going to happen, which means that that means that after 24 applications of the shift map, the image of S star is going to be within a distance of 1 over 2 to the 4th, or 1 over 16, of the period 4 orbit 1001 bar. Right? So in general, I will be able to include any possible starting sequence of n digits. And in fact, if I shift enough times, then I can shift this this S star. So I actually have that backwards, don't I? Yeah, so S star should be the thing that I'm shifting. And I'm trying to get close to T. There we go. That works better. So I'm going to shift S star some number of times so that I make it line up exactly with the first few digits of T. And that T was arbitrary, so I mean I can go ahead and do this for an arbitrarily large number of, or an arbitrary starting sequence of digits. So that means that S star has an orbit that gets arbitrarily close to each and every element, each and every sequence of sigma. Therefore, this orbit is dense, and sigma will be transitive. Right, and the final thing that we have to show is that the shift map actually demonstrates SDIC. So there actually is a paper from 1992 by Banks et al. That actually says that properties 1 and 2, which we have just shown, are actually enough already to imply that the shift map exhibits SDIC. But we're going to show this more precisely, or we're going to show it anyway, so we can get a more precise definition of what it means for a system to exhibit sensitive dependence on initial conditions. And we're going to take this definition down here for maps. Right, this actually comes out of Hirsch, Smale, and Devaney, so I'll even put that in here. Definition comes from Hirsch, Smale, and Devaney. And the idea behind this definition is that there is some sensitivity constant, they call it. This beta is some positive number such that if you go ahead and take S here to be some element of your space, and whatever open neighborhood you want of that element, whatever point, I'll call this T, whatever point that you have inside of this set U, however close you want S and T to be to one another, there is some other, oh shoot, is that right? Yeah. There is some other itinerary that, such that if you iterate these shift map on S and T respectively, that eventually the distance between them actually exceeds this sensitivity constant beta. So no matter how close S and T start to one another, there is some arbitrarily large number of iterations that you have to create, or some number of iterations you have to do on the shift map. But there is some large number of shifts that you can make that will send these guys at least beta apart in that sigma space. Therefore, our objective is to find an appropriate sensitivity constant. So why not just go ahead and make beta equal to the diameter of this system anyway? Maybe not the diameter, but this is the maximal distance between any pair of elements of sigma. So in order to show this, what we're going to wind up doing is creating the not function, right? And this C hat is effectively just telling us that whatever C is as a binary digit, we are flopping C to the other digit. So if C is equal to 1, change 1 to a 0. If C is equal to 1, if C is equal to a 0, change it to a 1. So what we're going to do is create, for any itinerary, whatever sequence here, S in sigma, we can construct a neighboring itinerary, some guy that is very close and agrees with S in the first n+1 entries, but then we say make it exactly the opposite of S for all digits thereafter, all digits thereafter. That means that not only do I get the distance less than or equal to this 1/2, I actually get a distance exactly equal to 1/2 to the n. And the distance between whatever the shift that I want here is that after n digits, right, after I shift this guy, I think I have to shift him n+1 times actually. Yeah, n+1, there we go. After I shift this guy n+1 times, then I have a sequence and it's dual, right? That these two orbits are actually now completely opposite to one another and achieve the maximal distance in sigma. Therefore, these guys are they exceed the sensitivity constant after n+1 iterations of the shift map. So such a T definitely, so for whatever neighborhood I want of S, certainly such a T exists because of the nature of how small I can make that distance. Right? I can make this arbitrarily small by making n arbitrarily large. Therefore, we have satisfied this definition from Hirsch, Smale, and Devaney, and that means that the shift map does indeed exhibit sensitive dependence on initial conditions. So we've satisfied conditions 1, 2, and 3, which means that we have shown that sigma, the shift map, is chaotic. Not only that, it is conjugate to the logistic map whenever R is greater than 4 and restricted to this set lambda, the non-escaping set. Because these guys are, because sigma is chaotic and conjugate to F, the logistic map itself, must be chaotic on lambda. So that is the power of shifting into or moving into a different phase space, something that's a little bit simpler to work with, especially from the standpoint of being able to represent elements. in an easier and more explicit way. So showing that you get equivalent dynamics on different spaces is a viable strategy in order to show chaotic dynamics, especially if you know or recognize those dynamics in other systems. So we would like to be able to have some rigorous proof behind that, and this is one of the major ways that we do it. And we'll see that a little bit more in our final video. As we end this one, we will be discussing one of the most ubiquitous objects in dynamical systems theory, the Smale horseshoe.